Imagine a statistical problem so complex that its solution seems to lie in a multidimensional labyrinth, a space so vast and intricate that calculating your way through it is practically impossible. This was the daunting reality facing physicists in the 1940s, trying to understand the behavior of neutrons in atomic fissile material. The mathematical integrals involved were simply too unwieldy. Welcome back to the podcast that tells the epic stories of the ideas that shaped data. I'm Arthur Pendleton. Today, we journey into the heart of one of the most powerful tools in modern statistics, the Metropolis-Hastings algorithm. We'll trace its surprising origins in the shadow of the atomic bomb, its decades-long slumber in obscurity, and its eventual triumph, a triumph that, as we'll see, depended as much on the rise of the desktop computer as on the brilliance of its creators. So stay with us for a story that connects the most theoretical of mathematics with the most practical of revolutions. Our story begins not in a statistics department, but at the Los Alamos Laboratory in New Mexico during the height of World War II. Here, scientists like Nicholas Metropolis were grappling with the immense computational challenges of the Manhattan Project. Annoyed by slow, clunky calculators, Metropolis and colleagues like John von Neumann dreamed of faster electronic machines. After the war, Metropolis led the design of the first programmable supercomputer, which he wryly named MANIAC. With this new power, a new philosophy of computation blossomed, the Monte Carlo method. The idea, introduced by Metropolis and Stanislaw Ulam in 1949, was elegant in its simplicity: to solve a complex deterministic problem by using random numbers and probability. But the landmark moment arrived in 1953. In a paper focused on the physics of molecular states, Metropolis, along with the Rosenbluths and the Tellers, described a specific method that was a leap beyond simple random sampling. They were trying to calculate a complex function of energy for a system of particles. The naive Monte Carlo approach was inefficient, as it would most often randomly pick configurations of particles that were highly improbable and thus useless for their calculations. Their brilliant insight was to turn the problem on its head. Instead of choosing configurations randomly and then weighting them, they devised a method to choose configurations with a probability proportional to their importance. Think of it not as throwing darts blindly at a dartboard, but as a clever way of biasing your throws towards the bullseye, learning from each previous throw. They would propose a small, random move for a single particle. If this move lowered the energy of the system, it was always accepted. If it raised the energy, it was only accepted with a certain probability. This simple accept-reject rule, repeated over and over, ensured that the system would eventually settle into, or as they said, become ergodic toward, the desired equilibrium distribution. It was, in essence, the birth of simulated annealing, and, though they didn't call it that, a Markov chain Monte Carlo method. For decades, this Metropolis method languished, known mainly to specialists in mathematical physics. It was like a powerful engine waiting for the right car. It was a professor from the University of Toronto, W. Keith Hastings, who finally built that car in 1970. Hastings saw the algorithm not just as a tool for physics integrals, but as a general method for sampling from any complex, high-dimensional probability distribution. He generalized it, allowing for a wider range of proposal mechanisms. His statistical reframing, speaking in terms of Markov chains and invariant distributions, was crucial, and as any good statistician does, he compared his method to a competing one from A. Barker. Hastings shrewdly suggested his was better, a hunch later proven with mathematical finality by his student P.H. Pescun. Yet, even with this theoretical seal of approval, the algorithm remained in the wings. What finally brought it to center stage? Two things. First, the rise of its cousin, the Gibbs sampler, in the early 1990s, which opened statisticians' eyes to the power of Markov chain Monte Carlo. Second, and perhaps most importantly, the personal computer. As one reviewer noted, by the early 1990s, large numbers of researchers could finally implement these demanding algorithms on their desktops. It was a godsend, particularly for Bayesians, freeing them from the shackles of conjugate priors and allowing them to simulate from previously intractable posterior distributions. The Metropolis-Hastings algorithm had at long last reached the mainstream. So, the journey of the Metropolis-Hastings algorithm teaches us a profound lesson: that a brilliant idea can remain dormant, waiting for the right language and the right technology to unleash its potential. It's a story that began with the immense calculations behind the atomic age and now lives on in the Bayesian analyses, running on the laptop of every modern statistician. It's a testament to the fact that the tools which shape our world often come from the most unexpected places. Thank you for joining me on this journey through the history of data. If you enjoyed this story of a brilliant insight, there are many more episodes waiting for you. Until next time.